Okay, so let's get started. We're very happy to have Shota Komatsu, who is telling us about how planar n equal 4 superangles is generating theory for integrable systems.
Okay, thanks for the introduction, and then thanks for the invitation. This is my first time to come to GGI. So today I'm going to give an overview about planar n equals 4 superangles theory and the relation to integrable systems. So basically, I'm going to spend my talk just explaining what I mean by this sentence. So that's basically the goal of my talk. Okay. So, but of course, there are many jargons in this sentence. So I first need to explain what I mean by this sentence, and I need to explain the meaning of the jargons. So let's start with the 4. 4 is quattro. But unfortunately, this is where my knowledge of Italian stops. So let me just move to here, SYM. So what is SYM? So SYM is just an abbreviation of super YAMLs. So this is a supersymmetric version of YAML theory defined in 4 dimensions. As you probably know, the action of the YAML theory typically takes this form. Well, actually, let's just write a Lagrangian, which is 1 over GML squared times trace F mu nu, where F mu nu is del mu a nu minus a mu del nu plus a mu, the commutator term. So what's important here is that a mu, so I'm going to talk about super YAMLs with the gauge group SUN. So roughly speaking, you can think of this A mu as like coming with extra indices AB, which runs from 1 to n. So like roughly speaking, these A mu gauge fields are kind of n times n matrices, okay? So this is just the usual YAML's action, but what makes it super is that it also comes with bosons, actually, 6 bosonic field phi's, and then 8 fermionic, 8 fermions size, okay? And if you count the number of degrees of freedom, we have 6 boson. And in addition, we have 2 bosonic degrees of freedom from the gauge field. So the gauge field has like index mu runs from 1 to 4. This is the space-time index. But because it's gauge fields, like actually the physical degrees of freedom is just 2. And then summing it up, then you get 8. And you can also see that there are 8 fermions. So the number of bosonic degrees of freedom and the number of fermionic degrees of freedom precisely match. And that's one manifestation of the supersymmetry, okay? But there is one more important consequence of the supersymmetry. So because all these fields, bosons, gauge field, and fermions are related by the supersymmetry, actually all these fields, for example, bosons, are also n times n matrices. So more precisely, in terms of mathematical language, they are basically in the adjoint representation of the gauge group. So these, sorry, n and b also runs from 1 to n, okay? And so is fermion. So now let me just come back to this n equals 4. So n equals 4 means that we actually have 4 sets of supersymmetry, and having 4 sets of supersymmetry allows you to relate fermions, bosons, and gauge field, and that's why everything is in that joint representation with a gauge group. Okay? So now I also need to say a few words about what I mean by gauge theory. So of course there is a more like mathematically rigorous definition of the gauge theory, but in my talk what's important is that all these fields, for example phi, are subject to the identification G phi G inverse, where G is element of the SUN group, and it can also be space-time dependent. And only things that are invariant under this identification are physical observables. Okay? For example, the simplest way to construct a physical observable then is to take, for example, phi1 inserted at x, phi2 inserted at x, and phi3 inserted at x. So this 1 to 3 is just like I just took like a 3 scalars out of 6 scalars, and consider everything at the same point, and then multiply them, and then take a trace. Then you can see that gx and g inverse x just cancels out in this definition. So that's why this defines you a physical observable. Okay? So this is often called a single trace operators. And that's mainly the main character in my story, in the talk today. Okay? So now, let's move on to the first word, planar. So what do I mean by planar? So planar, or more precisely, planar limit, is some simplifying limit of n equals 4 super Mills theory, or more generally, SUN gauge theory, or like it's also known as like a large n limit. So let me just gives you a definition. So the planar limit is defined in the double scaling limit in which n of SUN goes to infinity, while keeping GM Mills times square times n, which is often called a 't-Hooft coupling, and we often denote it by lambda, fixed, or more precisely finite. So this is a double scaling limit in which you send n to infinity and GM Mills to 0. Okay? So what's special about this limit? So in order to see what is special about this limit, let me just remind ourselves about the Feynman diagram computation of the field theory. So if we consider, for example, phi cube, usual phi cube field theory, then of course like a typical diagram that you draw is that we have 3 vertex, which comes from the phi cube interaction. And then, well, you, for example, connect it in some way to construct like a vacuum bubble diagrams, which computes the vacuum energy of the field theory. So this is what we normally do in the Feynman diagram. But as I said, in this n equals 4 super Mills theory, or in gauge theory, in addition to like the field, the indices which label the field, we also have this gauge group indices, which runs from 1 to n. So it's more natural to replace the propagator with a double line so that we can also keep track of these gauge indices. Okay? So now let's do this and then draw some kind of like a Feynman diagrams. The simplest Feynman diagram that I'm going to draw is something like this. So this is just a double line version of this diagram, which you will draw in the phi cube theory. Okay? And then let's see what happens to this diagram if you take this limit. So remember that all these lines are labeled by extra indices which runs from 1 to n. And in particular, if you look at this line, then there is a closed loop made out of this like extra index b. And that gives a factor of n because we are basically, closed loop means trace. So we are taking a trace of this like a color, what we call color index. So this gives you a factor of n. And this also gives you a factor of n because again we have a closed loop, and then we have also closed loop here. And also outside there is a closed loop. So in total we have n to 4 closed loops. So that gives you a factor of n to 4. And in addition, we used interaction vertex 4 times here. And each interaction vertex comes with GM Mill, 1 power of GM Mills, because it's interaction, the GM Mills is the interaction coupling constant. So in this limit, this diagram scale like n to 4, GM Mills to 4. Okay? So this basically gives you, in terms of this tofu diagram, tofu coupling, n square times lambda square. Okay? So this is the scaling of the one particular diagram that I drew. So now let's draw another diagram. Which is of this form. So instead of drawing that one, now I'm going to consider this one. No. This one, okay? So this is the n equals 4 version, the gauge theory version of this diagram in the phi cubed theory. So now let's do the same counting here. So first of all, we are again using 1, 2, 3, 4 interaction vertices. So that gives you GM moves to 4, okay? But on the other hand, if you start counting the loop, then this goes like this, and this goes like this, and goes like this. And actually, there is only a single loop inside. And then there is yet another loop outside. So that gives you a factor of n squared. So now, in terms of two-foot coupling, so this is just lambda square. So now it's clear that in the large N limit, we can basically forget about this diagram and just focus on this diagram. So this is basically the word planar comes about. So this, in terms of graph, this is a planar graph, by which I mean this is a graph that you can draw on a plane. On the other hand, this is non-planar because there is a lines crossing, and if you really want to draw it, then you actually need to draw it on a torus. So this is where the planar limit helps us to simplify the computation. So to summarize, if you take this double scaling limit, we can actually focus on subset of diagrams, which corresponds to planar graphs. Okay. So any questions so far? So now, I'm going to move to the connection to the integrable system. So the connection to the integrable system shows up in the computation of two-point function, single trace operators. So let's consider the two-point function, which is space separated by in space. So let's take one operator like this. So this is precisely the operator that I introduced. And then let's put another operator, again, given by trace. So now I want to put it on another point. Okay. So now, to simplify our argument, let's focus on the computation of the two-point function of these operators, each of which contains a lot of scalar field in the limit. At tree level of the gauge theory. So by tree level, I mean we keep the quadratic part of the Lagrangian, so the computation can be done by just doing the weak contraction. So in order to do that, let me just introduce a graphical notation of these single trace operator. So in single trace operator, the important point is that if I were to reintroduce the gauge indices, then these gauge indices are contracted because we are multiplying the matrices, okay? And the way to express it in terms of the picture is like this. So we first consider I1, and then I2, and then And then, so this means that this line means that we are like a B and B are identified. And then in the end, we need to take a trace. So that forms a closed loop. So let me just, sorry for erasing this, what I just wrote. But so that forms a closed loop. So IL. So this gives you some kind of like a closed loop in terms of gauge indices. Now, what I'm going to do is to prepare these two closed loop. So we also need to have yet another loop here. And then start doing the weak contraction using the propagator, which is again given by double line. So there are several ways to do that. The simplest way is to just like do something like this. So let's just consider for simplicity the case where you have like only 2 fields inside a single trace operator. And no, 2 is not good, so let's consider 3. Okay, so this is good because as you can see that this is a planar diagram that you can draw on the plane. On the other hand, you can imagine doing the different with contraction in which you connect these fields with these fields in the operator 2. But that is suppressed, again, because there is a crossing of the propagators, and that is actually suppressed by one factor of 1 over n squared. So if we focus on the planar limit, essentially, we need to just consider this ordered weak contraction, in which you keep the order inside the single trace operators. Okay? So, but of course, like this is just a treatable weak contraction and nothing is interesting. But something interesting starts to happen if you start including interaction and doing some perturbative computations. So what happens? So let's consider like some interaction vertex. For example, I can imagine connecting these two guys with some exchange of some extra fields. So of course, at one loop, so if you start including interaction, so this gives you a factor of g m mu square, and it also increases a factor of n. So this diagram shows up in the perturbative expansion at the leading order in lambda. Okay? So this basically connects or like produces some interaction between fields living here and fields living here. Okay? And I should also mention that again, the same comment about the planarity applies here as well. So for example, you can imagine doing the contraction between this guy and this guy. But that is suppressed, again, because this is not planar diagram. So essentially, what planarity means in this context is that there is always, at least in the leading order in lambda, the nearest neighbor interaction. So now I introduced the notion of ordering and a notion of nearest neighbor. Now things started to smell a bit like a spin chain. And indeed, that is what people actually found by doing the perturbative computation. So that was found in 2002 by Minahan and Zarembo. So let me just state what they found. So they considered the two-point function of single trace operator. And this two-point function, so some O and O prime, in n equals 4 supermills, I didn't explain this in detail, but n equals 4 supermill is known to be conformal field theory in 4 dimensions. So this two-point function of single trace operator behaves like power law at any distance if you pick appropriate operator, single trace operator O. And now the important question in this two-point function is to compute this delta, coefficient delta. Okay, so and then this delta is in general depends on the coupling constant lambda, which is the two-foot coupling constant. And then they asked, like, what is the leading coefficient at one loop in lambda? So they basically just did a computation using the perturbative analysis, and they found something interesting. So they found that, so in order to explain what they found, let me just consider a simple class of single trace operators in which operator is made out of just two complex scalar field. So let's consider simple class of operator in which operator is made out of two complex scalar fields. So this is like a phi 1 plus I phi 2. And this is like a phi 3 plus I phi 4. So what they found is that take this operator and then map it to the spin chain state where you view Z as upspin and X as downspin. So then like this state gets mapped to this spin chain state. And under this mapping, you can rephrase the computation of this object, the computation of delta lambda, in particular the leading term, to the computation or diagonalization of the spin chain Hamiltonian. And what was remarkable was that this spin chain Hamiltonian happened to be the simplest possible integrable Hamiltonian, which is precisely the XXX spin chain, or Heisenberg spin chain. So now we are in business because we know how to diagonalize this Hamiltonian and then compute the energy eigenvalue. So this basically maps to the energy eigenvalue. Yes, please ask. Yes, yes. Okay, so actually overlap between the state get mapped to the overlap between the state and the spin chain. But here, like we are talking about energy eigenvalue. So the map is that, okay, let me just say. So there is, in principle, I didn't explain it, but in principle, there is also some normalization here. And that is mapped to the overlap between the spin chain states. But this coefficient is mapped to the energy eigenvalue. Oh, like you were saying, like which energy eigenstate we should take? Well, basically we can take like any energy eigenstate, and that corresponds to, so basically because this mapping is really like precise, so once you construct the beta eigenstate, that gives you some kind of linear combination of this kind of single trace operator, and all of them have a nice property, like if you separate the two object, then it has like a simple power law. And if you don't take that linear combination, then you just get a mess, like a sum of power laws with different powers. So in terms of conformal field theory language, this operator, which comes with a single power law, is called the primary operator, conformal primary operator. Okay. So this is what they found. And then people also started, so this is just like one loop computation, and then people started asking, what happens if you do the two loop computation, which is proportional to the coefficient lambda square? And already in this picture, I can predict what's going to happen, at least qualitatively. So if you start considering lambda square, I can add another bridge here. Okay? So this gives you GM is GM mil square. So that gives you another factor of lambda. So clearly from this picture, now if you go to the two loop, the spin chain becomes next nearest neighboring. And indeed, people did that computation and mapped the computation to the spin chain and found a next nearest neighboring interacting spin chain, which again happened to be integrable. And people also did in some cases for the 3 loop, I guess. And again, it was also integrable. So essentially, what they found is that by doing this computation in n equals 4 supermills, we keep finding an integrable spin chain. And in particular, we actually keep finding long-range interacting spin chain. So let me just draw this picture. So here we have an axis of lambda, so where we have lambda equals 0, and we have lambda equals infinity. And as you increase, so as I was saying that here, at one loop, we have like a nearest neighbor spin chain. And as you increase the perturbative order, or the loop order, then nearest neighbor spin chain becomes long-range spin chain. But still, it preserves integrability for some mysterious reason, which we don't quite understand yet. So this is what people observed from this like gauge theory side. But there is also yet another story. OK, I have 15 more minutes. 20, OK. So there is yet another story which actually relies on what's called Adscft correspondence. So this part I'm not going to explain much. But basically, this n equals 4 supermill theory in planar limit is supposed to be dual to string theory living on ADS5 times S5 spacetime. That's like a higher dimensional spacetime. And from that point of view, what we need to study is a sigma model, 2D sigma model, which describes the string dynamics in ADS, whose target space is ADS5 times S5. And this lambda going to infinity limit corresponds to the classical limit of the string sigma model, which you can show to be integrable. So this model is classically integrable. And as you decrease lambda, from this language, this corresponds to quantizing the sigma model. And in particular, if you really want to go to lambda equals 0 limit, this is going to be highly quantum sigma model. So here, something interesting is happening. So if you believe in Adscft correspondence, these two descriptions must give the same answer, which means that actually, so take the spin chain and then making it to very, very long range. And once it becomes like a very, very long range, it must be equal to the 2D sigma model. And on the other hand, if you take 2D sigma model, which is classically defined and integrable, and then quantize it, and in the limit in which it becomes highly quantum, and highly quantum roughly physically means that string starts like oscillating widely. And in that limit, it should reproduce a simple spin chain. So we don't quite understand why this is happening, but let me just emphasize one point. So I guess in condensed matter physics or statistical mechanics, it's very common to have take some spin chain and then take a continuum limit in which the length of the spin chain becomes very large and look at the low energy excitation, and that's effectively described by the sigma model. But that's not what's happening here. The claim is that long-range spin chain, which is defined on the discrete side, is exactly equal to the 2D sigma model in this weird target space. So that sounds very odd. And in the sigma model, it's like essentially like a vertex operator or a state on a cylinder. So you quantize a state on S1 times R, and then compute the energy of excited state on S1, which in principle you can imagine doing the computation using thermodynamic Bethe-ansatz, and that should reproduce the same answer as the long-range spin chain. So there are some, well, to be honest, like I should say that we don't quite understand why this is happening physically, but there are some interpretation why this is happening, or like what's, like qualitatively, what's the relation between the two. So one proposal advocated in the past is that, so one difference between spin chain description and the sigma model description is that sigma model description is two-dimensional relativistic theory on the worldsheet. So it has particle and antiparticle. Whereas this long-range spin chain is more like a deformation of the XXX spin chain, so especially the ferromagnetic one. So there is no antiparticle. We have just like an upspin, and then there are magnons, which describe the propagation of downspin. And in addition, to the sigma model, if you just write down the Lagrangian, like it's described by local Lagrangian in 2 dimensions, whereas this one is clearly non-local. And one proposal people made is that take the 2D sigma model and describe it, like split the degrees of freedom into particle and antiparticle, and then in some sense integrate out antiparticle degrees of freedom or negative energy model of the degrees of freedom, and that effectively makes the sigma model long range. And that is one possible way of relating to the sigma model to the long-range spin chain. But that was just like a very vague idea. People did some computation, but no one has really succeeded in making it precise. Okay, so this is one place in which you can see that n equals 4 super mills acts as a generating system of the sigma model, sorry, of the integrable system. So let me just give you another example. So another example is a 3-point function of n equals 4 super mills. So before I was talking about the 2-point function. So let's say now we want to analyze the 3-point function. We are just going to do the same. We take like a 1, 2, 3 single trace operator, and then compute this expectation value. So again, n equals 4 super mills theory turns out to be, because it's conformal field theory, 4-dimensional conformal field theory, space-time dependence of this 3-point function is completely fixed. So if you're familiar with the 2D CFT, then space-time dependence is essentially more or less the same as the 2D conformal field theory. And the non-trivial information sits here, which is often called a structure constant. Or fusion coefficient, or OP coefficient. It comes, yeah, different people call it with different names. But the summary is that what's important here is that all the dynamical information of the theory is encoded in this single scalar function. Because we already know what these powers are from the study of the 2-point function. Okay, so now let's see what we will get. Again, doing some weak coupling computation, or like a weak contraction computation. So again, we have some 3 operators which I expressed in terms of these graphical notation, and then I start connecting them so that it becomes planar diagram. So one way of connecting them is like this, right? And then connect it like this. So now, what people found is that this computation can also be phrased in the spin chain language. So how do you rephrase this computation to the spin chain language? As I was saying before, there is a precise mapping between the operator and the spin chain eigenstate. So what we basically need to do is to take some spin chain eigenstate, psi1 and psi2 and then psi3, and then cut the spin chain eigenstate here into two halves. So originally the state was defined on the length, in this case 5, but then I cut the spin chain eigenstate into the length 3 part and the length 2 part. And I do the same here. So then each spin chain eigenstate gets replaced by some entangled state of, like in this case, like initially it was defined on the length 5. Now it gets replaced with some entangled state of length 3 and a length 2, and we need to sum over all possible psi1, phi1, and phi1 twiddle. So after doing this cutting, then what we need to do is to, well, we basically do the same cutting here and here, and then take the overlap between, because computing this part is basically taking the overlap of the spin chain state. So that gives you like a complicated sum, phi1, phi1, phi1 twiddle, phi2, phi2 twiddle, phi3, phi3 twiddle, and then phi1, phi2 twiddle, phi2, phi3 twiddle, phi3, phi1 twiddle. Okay, so this is essentially the computation one needs to do, which looks horribly complicated. But there are some simple cases in which the computation reduces to known object. For example, in 6-vertex model. In particular, there are situations in which the computation reduces to what's called partial domain wall partition function. So what is that setup? So the setup is that we take non-trivial spin chain eigenstate for the operator 1, which is a complicated combination of up spin and down spin. And for the operator 2, we take an operator which is just dual to spin chain, which just corresponds to ferromagnetic vacuum. Okay? So that's the operator 2, which is very simple. And for operator 3, we have, let's take this one. It's a simple combination, again, simple product state. But now we take this combination. So this is just like a rotated ferromagnetic vacuum. Okay? So now let's try to do this computation. So this overlap between this operator 2 and operator 3 are simple because it's product state. Because it's product state, even after you cut it, you just get one term. And for each one term, you just get like 1 over square root of 2. So, and this one, so then like a non-trivial part only comes from this part and this part. And this is essentially an overlap between this spin chain eigenstate and up spin to the power. So let's call this length L, this length L, and then this length L1 minus L. I'm assuming that the original spin chain is length L1. So here I have L1 minus L, and then I start having up plus down over square root of 2 to the power L. Okay? But this looks a little bit complicated, but what this tells you is very simple. So whenever you have downspin, in order for this overlap to be non-zero, like a downspin in this spin chain eigenstate must always be on the side L1 minus L plus 1 to L1. Because otherwise, this projects out and gives you 0 result. So basically what you need to do is to decompose this spin chain eigenstate, which is given by the beta eigenstate, and then just keep the term in which the downspin lives on the side L minus L plus 1 to the side L1. Okay. And this can be done using the well-developed techniques of spin chain. And in particular, by mapping to the 6-vertex model, you can map it to the what's called partial domain wall partition function, which has a nice, which was studied by Folda and Wheeler, and also other people, and which has a nice determinant expression. But in particular, for our purpose, what's used for is this representation. So let's consider the beta state which are labeled by the rapidity u's. And let's take that to be operator 1. And then the expression is given, and the result we get is this. So we take sum over partition of the rapidities, and then multiply -1 to alpha bar, which is the number of elements in alpha bar, and then consider this sum, j belonging to alpha bar, and uj plus I over 2 over uj minus I over 2 to the power L, where L is essentially how we split the spin chain into L minus L and L1 minus L to small l. And then the final thing is j belonging to alpha, k belonging to alpha bar, and it's uj minus uk over uj minus uk plus I. I guess, of course, I'm just rewriting the partial domain wall partition function, so probably for many of you, I think this is a kind of familiar expression. Oh, so this is just another representation, and you can also rewrite it into determinant. Okay, so this is the structure we get by using the techniques from the gauge theory side. And again, here, we can, so this was just a tree-level computation, and then we can ask what happens if you start including loops. And people did the computation, and then essentially what people found is that this structure, this oval structure, is not modified even if you include 1-loop and 2-loop interaction. And the only difference is that now this part gets modified into some non-trivial function of f uj, which now depends on the two-foot coupling lambda. And this part also gets modified into some non-trivial function, which only depends on uj and uk and the two-foot coupling lambda. So this is just an empirical observation. But now, again, Adscft helps you to understand what's happening, or what's the underlying mechanism. So the underlying mechanism is the following. So again, I'm going to draw this picture. So when lambda is 0, we had this this overlap of the spin chain state. On the other hand, the analogous object on the string theory side is actually integrable sigma model now living on a pair of pans. Okay, you can see that topologically this picture is the same as this picture. And so this integrable sigma model living on a pair of pans is not something people studied a lot in the literature, but at least Adscft tells you that's the object relevant for this guy, especially when lambda is infinity. And as I said, this object is not something people often talk about in the integrable system, but there is actually an analogous object people studied in the past in the context of integrable field theory, which actually shows up in the computation of entanglement entropy. in the integrable quantum field theory. So because I'm running out of time, so let me just give you a qualitative picture. So now I want to study integrable sigma model living on a pair of pants. But this pair of pants geometry is intrinsically finite size. And typically, if you want to study integrable quantum field theory, it's better to first go to the infinite volume limit and describe it in terms of matrices, and then later compactify or include a finite size effect using the technology like thermodynamic Bethe-Anders. So then the question is, how do you decompactify this pair of pants? And in order to understand it, you just need to look at pair of pants you are wearing. And if you look at the pair of pants you are wearing, there are basically 3 seams. And if you cut your pair of pants along those 3 seams, then it breaks down into 2 hexagonal patches. So this is roughly the basic object which we should analyze in the infinite volume limit of the pair of pants, which we call hexagon. So this object still looks very different from what people study in entanglement entropy. But let me just say the following. So instead of hexagon, so now from now on, I'm going to just draw a bunch of pictures in the remaining 1 minute or 2 minutes. Instead of hexagon, let's draw octagon. Don't ask why. Now, I'm going to claim that this object is the same as this object. So this is a square root branch cut. So this is because this is a square root branch cut. If you cross this, then there is another sheet. Okay. So the precise correspondence is the following. So you take this edge corresponds to this edge, and then this edge corresponds to this edge, and then so I'm going from here to here, and then let's go from here to here. Then I need to cross this branch cut and re-emerge here. And then I have this line, which corresponds to this line, and then finally comes back to this line. Okay? So this is just a picture, but just to show that what we are talking about here, which is octagon, is nothing but the two-sheet integrable field theory living on the two-sheeted geometry. And this is precisely what people need to compute if you want to study the Renyi entropy, in particular what's called Renyi 2 entropy, which is roughly speaking a trace of rho A square, where A is the subregion density matrix. So I don't have time to explain it, but probably some of you are familiar with this concept. Now, there is a very nice work by Carl D. Calabrese and Doyon. I'm not sure if I remember all the authors, which basically formulated the form factor bootstrap approach to compute this Renyi 2 or Renyi n entropy. So in their paper, they basically analyzed the case where this 2 is replaced by some arbitrary integer n. Now, from that point of view, the hexagon that we need to analyze is actually a weird object, which I would call Renyi 3/2 entropy, which is a very unnatural from the entanglement entropy point of view, but still you can actually adapt the form factor bootstrap axioms to this context and compute and determine what this object is. And in particular, if you do that computation from the string theory point of view, and then you discover that you can actually determine this two-particle form factor, ui and uj, as a function of two-foot coupling. And this h, if you take lambda going to 0 limit, precisely reproduces this object people discovered from the spin chain computation. So this is another instance in which you can actually see the equivalence between sigma model and the spin chain. And in particular, thinking in terms of sigma model helps because in the sigma model, there are like you can formulate the form factor bootstrap axioms and directly try to compute this object, for example, using crossing symmetry and Watson's condition. Whereas in the spin chain context, well, the direct analog of that is not known because there is no antiparticle. And a similar idea was, I think, explored in the past by Musardo and his collaborators by taking the non-relativistic limit of the Sinch-Gordon and to get to say something about Lieb-Liniger. So what is happening here is a little bit similar, but slightly in a different context. So, okay, so because I'm over time, so let me just finish it.
Okay, thanks a lot, Shota, for the inspiring talk. Any comments or questions?
Sorry, I have a very stupid question. Integrability, Bethe-Ansatz integrability is rooted in the fact that you have a 1 + 1 dimension.
Yes.
Here, the dimensionality is played by the planar limit or by something else?
Right, okay, so the dimensionality, so two-dimensionality basically shows up, as you said, like coming from the planar limit. Because it's planar, like there is a natural two-dimensional object showing up.
More questions?
Yeah, maybe it's not important, but you explained in this picture that you must have like eigenstates. And now you're computing for these 3 states. Out of 3, only 1 is eigenstate. So is it okay?
Okay.
Yeah, because from conformal primaries, right?
Right, so but you know, like this is the eigenstate of a Heisenberg spin
Yeah,
but this one is actually also eigenstate of a Heisenberg spin chain because you can get this one from this one by just doing the SU2 rotation. And the Hamiltonian commutes with SU2 rotation.
Okay.
Yeah, just to follow up a little bit. So here you can in principle choose different eigenstates, I guess, because this is studied by Slavnov, right, called two-component model or something.
Right, yes, exactly.
So yeah, but there I'm not sure if there's a nice formula as this though.
Yeah, so I think in some sense, like this is you can also rephrase it in terms of Slavnov determinant, but it's a kind of very simple case of Slavnov determinant because what's showing up here is a very particular state, not just a random like offshore beta state. And for the Slavnov, I think like you can still express it as a sum over beta roots, but in general, the expression showing up as a sum is more.
I think it's similar. You also need to kind of partition your beta roots into two sets, if I remember correctly. But
yes, exactly. But I think the summon is more complicated.
Yeah, absolutely. Yes. Okay, thank you.
Okay. I don't see any more comments or questions, so let's thank Shota.